This is the Discovery Files podcast from the U.S. National Science Foundation. When the sun and the moon align, the moon blocks the sun's light, resulting in a solar eclipse. Throughout history, people have sought to understand the phenomena. A partial eclipse is depicted on the tombs of Ramses V and Ramses VI in Egypt, interpreted by the Greek historians as omens, and in an ancient Chinese tradition, focuses on a hungry dragon that is trying to eat the sun. We are joined today by Carrie Black, a program director for the National Solar Observatory in the Astronomical Sciences Division here at the U.S. National Science Foundation. Dr. Black, thank you for joining us today. I'd like to start out with a little bit of background. What sparked your interest in astronomy?
When I was looking at careers in college, I thought string theory sounded really cool. And so I really wanted to study that. But to be perfectly honest, I found there were no jobs in string theory, or they were hard to come by. So that was kind of out for me. But then when I was in grad school studying plasma physics, I worked with a group that was largely focused on fusion, but also had some space plasma research. And that was when I started looking at the sun, looking at these really cool images and movies from the Dutch Open Telescope and the Canary Islands. Oh my goodness, like what the heck is happening? It was right around that time that NASA had launched the Solar Dynamics Observatory. And then we were getting really amazing movies of the dynamics on the sun. And that was amazing. That was really impressive. It made me want to study a star up close, This is so cool. Like, really? We can study one of these things? It's like right here in our faces? That's incredible.
Right. As the technology gets better and you can see these features that we barely recognized historically.
Yeah.
So what is the National Solar Observatory?
The National Solar Observatory is one of NSF's federally funded research and development centers. So it's a national center where they study the sun. We have telescopes actually all across the globe that are looking at the sun. So there are two major types of studies that happen at NSO. There's something called the synoptic program, which is basically long-term study where they are looking at the full disk of the sun, the full surface of the sun. They're looking at it in different wavelengths and the magnetic field. And we have 6 stations located around the globe so that 24 hours a day, we're looking at the surface of the sun. So it's very cool. You can build up this, from the 90s, we've built up this data set, daily measurements of the sun. And then the other type of measurement that we make is a zoomed in, and that's provided by the Daniel K. Inouye Solar Telescope. The Daniel K. Inouye Solar Telescope is the world's largest, most powerful solar telescope. It's got a mirror that is 4 meters in diameter. It's more than twice the size, more than twice the diameter of the next largest solar telescope, which also happens to reside in the United States. And it is so incredibly powerful. It can look at what are tiny regions on the sun, but still very large to us, with incredibly high resolution. And this is really unique and is going to get at some of the plasma dynamics that we haven't been able to study to date. It's able to look at both the surface of the sun and in the low corona, so very near the surface, which is really important because that area of the atmosphere has not been studied extensively because most occulting disks block out the low corona. What we're going to get from these high-resolution images is the ability to compare with our models. So for a long time, we've had simulations, models that theorize what happens on the surface of the sun, but we haven't been able to take observations that were at that resolution. And so we're finally going to be able to do that. And it's just groundbreaking and also incredibly complementary to the other types of telescopes that we have looking at the sun.
So we might have heard about a partial eclipse, let's say. What are the different kinds of eclipses?
A total solar eclipse is, I think, the most popular type. And that's when the moon passes between the sun and the earth, and the moon casts a shadow on the earth, and it blocks out the sun. And so you can just see the atmosphere, which is like diffuse and not as bright as the surface, but really cool to study. There are other types too. There's like a partial eclipse. A partial eclipse is when the shadow blocks out part of the surface of the sun. And then there are things like the annular eclipse. And that is when the shadow of the moon blocks out almost the complete surface of the sun, but not quite. And so it leaves a very bright ring that you can still see.
How do eclipses help us understand the sun? What can we only learn during that window?
Total solar eclipses are great for studying the atmosphere of the sun, or the corona, as we call it. They allow us to see the corona that you wouldn't be able to see otherwise because it's so thin and not nearly as bright as the surface of the sun. But we live in the atmosphere of the sun. The planets all exist in the atmosphere of the sun. So being able to look at it and see what's happening there is unique to total solar eclipses. We study eclipses, and we use the idea of an eclipse, an artificial eclipse, to study the corona through our telescopes, both the ones on the ground and satellites. And that's where you put something up, call it an occulting disk. You put that up to block out the surface of the sun so you can see what's happening in the corona. But the thing that's really cool about natural eclipses is that the moon perfectly blocks out the surface of the sun, so you can see very close to the surface. You can see low in the corona, and you can't do that with artificial eclipses. The occulting disks are too big, basically. So natural eclipses are still the best way to study the atmosphere of the sun.
What are the elements involved there? What is happening in the atmosphere of the sun?
So the sun and the atmosphere of the sun are plasma. So they're these collections of charged particles. And the atmosphere is in this very gaseous form, right? So there's all sorts of intense magnetic fields. It's one of the really, truly fascinating things about the sun is the complexity and intensity of the magnetic fields. And when you look at the corona, you can see structures like streamers or things called coronal loops, right, that kind of loop back down to the surface of the sun. Those are all magnetic features that have plasma flowing along it. So you can see those, and you can see things like coronal mass ejections, which are the big solar storms, right? The big, huge bubbles erupt off the surface of the sun. The corona is really an interesting place. It's really cool.
Why can't we observe with our naked eye?
This one is tricky because you should not look at the surface of the sun ever without eye protection because the sun is so bright, right? It'll burn your eyes. It hurts if you try to look at it.
Do you have a favorite fact about the sun?
Okay, this one is really hard. I had to think about this because I have very many favorite facts about the sun. The first thing is how amazingly dynamic it is. Go look at movies of the sun. They are so incredible. You can see sunspots up close. They twist into really complex features. They move across the surface of the sun. One of the things that really boggled my mind when I first learned about it was that the sun moves at different rates based on where you are. So at the equator of the sun, it moves way faster than it does up at the poles. And it's because it's not a rigid body. It's not like rock, right? Because it's this plasma, it's like this fluid. It can move at different rates. So I thought that was really cool. And that all ties into things like the solar cycle, which every 11 years, the magnetic field flips. So if you start out with something that has a magnetic field that's basically like a bar magnet, then it gets twisted up over 11 years and in part from this differential rotation, which is where the equator moves faster than the poles. Magnetic fields get really tied up and twisted, and then there's sort of a spring-like action that happens and causes the magnetic field to flip again. So I thought that was really cool, and that it happens on this time scale of 11 years. It's so fast, right? So we can experience it many times in our life. It's really, really cool. Another fact that I think is really neat about the sun is that the atmosphere actually gets hotter as you move away from the surface of the sun. So if you think about something like a fire or a heat source, when you move away from that heat source, it gets cooler, right? When you move away from the surface of the sun, it initially heats up and then eventually it cools down. And this is called the coronal heating problem. And scientists still don't really understand why that happens. It's one of the ongoing areas of research.
Like something to do with the plasma space, like the gases catching.
Yeah,
it's interesting.
Yeah, the energy propagation from the surface out. They have a lot of theories. Wave heating or like nanoflares. I love this idea that there are these tiny, tiny little solar flares basically that are going off kind of all the time that dissipate heat from basically allow it to move from the surface out into the corona in ways that we haven't been able to study yet. But the Inouye Solar Telescope might get at some of that, so we're excited about that.
There's a long history of superstition around eclipses. Why shouldn't we be afraid of an eclipse?
people should get out and see the eclipse. Go do it. Don't hide from it. Go enjoy. Even if you're in a cloudy place, it's still worth being out when an eclipse happens. So in 2017, I was in South Carolina and it was cloudy. Just as the eclipse was going to happen, it was cloudy, which was a bummer because I really wanted to see the corona. But it gets dark. Everything gets quiet. The mood just changes like so quickly. It's really, really fascinating experience. Yeah. My friends who have experienced them or who are eclipse chasers tell me it is just the most amazing experience to look up at the sky and be able to see the corona, be able to see that the atmosphere extends through your entire field of view. Everywhere you look in the sky, there is the corona. And I get kind of emotional talking about it. I've never experienced it because I can imagine that you're in this space and all of a sudden it's like, oh my goodness, we're not just sitting in a vacuum of nothing. There is so much that's here and we're in the middle of it. I think that's what really drives people to go travel all across the globe and see eclipses as often as they can. People are very concerned about eye safety, as you should be, but don't hide from it because of that. We have protective eye gear that people can get access to so you can look directly at it, but there are also other mechanisms for looking at the sun indirectly. So you can do something as simple as a pinhole camera where you just poke a hole in a piece of paper and hold another piece of paper behind it. And you can, if you line it up right, you'll be able to see the light shining through it. And then as the shadow passes, you'll be able to see on the sun, other paper you're projecting onto. You'll be able to see the shadow passing through the field.
That's what we did during the 2017 eclipse. Cut little holes in a sheet of paper and projected the results around the yard.
Very cool.
I remember being struck by the silence of the birds during the eclipse. We had a couple of trees around the house and they all stopped chirping, which I thought was interesting.
There are templates that you can find online too. So there are many ways to look at the eclipse. So please get out and go see it. I think it's a truly wonderful experience.
Special thanks to Carrie Black. For the Discovery Files, I'm Nate Potker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.